Hello and welcome to today's video. In this video, we're going to investigate Taylor polynomials a little further. In particular, we're going to discuss their approximation properties. So this section is called Taylor approximation. Now, the first question that we're going to investigate is, what can we say about the remainder of a Taylor polynomial? Of course, we'd like to have that remainder approximate, or to have that remainder go to zero. We'd like to have the Taylor polynomial approximate the function, so the remainder should go to zero, at least close to the point x star that we used for the Taylor polynomial. We'd even like to have a little more here. We'd like that remainder to go to zero quickly. And of course, quickly is only meaningful in comparison to how fast we approach our x star. So what we would want is for the remainder to converge to zero as x tends to x star. And we'd like for that convergence to be faster than x tends to x star. Now, in more precise mathematical terms, what we want to investigate is the following. So the question that governs all of this section is, what can we say about the quality of the approximation? And of course, it's only meaningful to investigate that close to the point x star that we use for computing the Taylor polynomials. Now let's first investigate the case of n equals 1. Now then we'd like to have a look at the remainder, R1, at a point x. And we'd like to compare that remainder to the difference of x and x star. And as I said, we are interested in the behavior of that term as x tends to x star. So the question is, what is this term? Of course, we'd like for that to tend to 0. And we'd like for that to tend to 0 faster than x tends to x star. So of course, this expression also tends to 0 as x tends to x star. And that means if this is faster in precise mathematical terms, we would like for this here to be 0. So we'd like for that limit here to be 0, meaning R1 of x tends to 0 as x tends to x star faster than x minus x star tends to 0. So we approach x star and the approximation quantity gets better faster than we actually approach x star. So let's have a look at that limit here and see if we can say something about it. Now, what is that limit? Well, we can know what R1 of x is, so we can just substitute that. R1 is the difference between the actual function value at x, so f of x, and the Taylor approximation T1 f at x, and the approximation point being x star. So that's what we want to investigate here. And we even know what the Taylor polynomial is, so we can just substitute that. We get fx minus the Taylor polynomial, that is f at x star, plus f prime at x star times x minus x star. And we need to divide all that by x minus x star. And as you can see already, what happens here is, well, what we get is the limit as x tends to x star of f of x minus f of x star divided by x minus x star. And then for this term here, the x minus x star will cancel out. So we're only left with f prime of x star that does not depend on x anymore. So we can just take that outside of the limit. So that means we can subtract f prime of x star here. And if f is a differentiable function, which of course it needs to be for the Taylor approximation to work, then this here, this limit, is exactly equal to f prime. So what we get here is, that is f prime at x star minus f prime at x star. And that, of course, is 0. So that approximation, at least for the first order Taylor polynomial, really works. In other words, we can express this function R1 of x in the form x minus x star times the function, let's call that also R1, but with a small r, R1 of x. And this function has the property that the limit of R1 of x is 0 as x tends to x star. So if we divide R1 by x minus x star, then this remains and the limit still goes to 0. That is what we want here. Now, of course, in a similar way, we can have a look at the case of n equals 2. Now for n equals 2, we'd like a bit more. What we want to have a look at is the term R2 of x divided by x minus x star squared. Right? We now have an approximation of order 2. So we'd like that to be even better, meaning the remainder should go to 0 even quicker. And the next stage here, the next logical stage, is that it should go to 0 quicker than this quadratic term goes to 0. So we'll investigate this limit here in particular as x tends to x star. And again, we can just write that out. So that's the limit as x tends to x star of f of x minus t2 of f at x star over x minus x star squared. Now, to make use of the properties of the Taylor polynomial, what we'll do now is we'll say, well, obviously, this here tends to 0. We all know that the Taylor polynomial has the property that at x star, it's going to be equal to f at x star. So this difference will also tend to 0. We don't know how fast yet, but it will tend to 0. So both this and this goes to 0. And that means we have an expression of the form 0 over 0. The functions, this one here is surely a differentiable function. F is differentiable, and the Taylor polynomial is a polynomial that's also differentiable. And this here is also a polynomial, so differentiable. And that means we can apply L'Hopital's rule to this limit here. So if we do that, what we get is, well, for the numerator, what we get is f prime of x minus t2 prime f of x and x star so the derivative of the Taylor polynomial. And for the denominator, we simply get 2 times x minus x star. And of course, we can do this once. Why not do it twice? Again, the denominator goes to 0. Here we have f prime of x, and here we have the first derivative of that Taylor polynomial, and we know that one of the properties of the Taylor polynomial is that the first derivative at the point x star is equal to the first derivative of f at the point x star. So again, this difference here will go to 0. So what we can do is we can again apply L'Hopital's rule, see what that yields, and what we get is, again, the limit as x tends to x star, f double prime minus t2 double prime f x x star. And for the denominator, we'll now simply get 2. And now we can easily make that computation. Of course, this limit of f double prime divided by 2 as x tends to x star, that will simply be the same thing as f double prime at x star over 2. And the limit of the Taylor polynomial, what happens here, of course, is this second derivative of the Taylor polynomial that agrees with the second derivative of f at the point x star. So we get the very same result here. We get this is minus f double prime at x star over 2. So again, the result here is 0. And what that means in particular is that R2 of x, the remainder of the Taylor polynomial of order 2, is of the form x minus x star squared times some function R2 of x, with the limit of R2 of x being 0 as x tends to x star. So in other words, the approximation is at least as good as this term here times some function that also goes to 0. So this here won't destroy our approximation properties. And of course, in the way that we've just seen with this L'Hopital's rule argument, this property can be generalized, and this leads to the first approximation theorem for Taylor polynomials. We, of course, need the usual provisions here. So let I be a subset of R, again, an open interval. And let F be a function on I mapping to R be n times continuously differentiable. And just as a reminder, this continuously differentiable, that is actually important because that's what we implicitly used here. In this step, the limit of f double prime of x as x tends to x0 is exactly f double prime at the point x star. That is, of course, only true if f double prime is actually continuous. So that's what we used here without saying it yet. So that is true as f double prime is continuous. And that's why we need this continuous differentiability here. Not just differentiability, but continuous differentiability. So function is n times continuously differentiable in I. And then we can say for each possible x star in I, there exists a function, and we call that Rn, defined on I with real values, with limit of Rn of x being 0 as x tends to x star. such that the remainder is of the form that we've seen above. So Rn of x is of the form x minus x star to the power of n times Rn of x. Or in other words, we can write the function f in the form Taylor polynomial of order n plus that remainder, and that is again of that form Rn times Rn of x times x minus x star to the power of n. That gives us at least a qualitative assessment of the approximation quality of our Taylor approximation. Now, of course, that is only true in the limit, so we don't really know how close we have to be to x star if you want a good approximation for whatever definition of good we use. So one other question is, can we explicitly bound that error for a given point? And this is something that this theorem does not provide, but there is a theorem that does provide just that. So the additional question would now be, provide possibly explicit error bounds for a given x in I. And there is a theorem that does at least part of that. Let's say it gives us a way of providing these explicit bounds, or at least getting a bound on these explicit bounds that can be useful for computing Taylor approximations. What we'd like to know, of course, is how large is the error if I'm that much away from the approximation point, from that x star. Or the other way around, if I want to guarantee that my approximation is within a certain error bound, what is the necessary degree of Taylor polynomial that I need for that? How far do I have to take this? And this next theorem provides us with a few hints on that can be used in many cases to give an answer to that question. And of course, also to the question of, does the Taylor polynomial converge to the function at all if we increase the degree sufficiently? That's something that we'll deal with in a later video. But for now, let's make this theorem more precise. Usual setup. Again, we'll need an open interval, so we'll start with I subset of the real numbers. Let that be an open interval. We need a point x star in that interval, and let f be a function on I with values in R. And now the difference to the theorem that we had before is we now want f to be at least n+1 times continuously differentiable. So once more than we've had before. And we want that to be continuously differentiable on I. Then we're looking at a certain point, and we want an approximation bound, an error bound of the approximation for that point. And what the theorem gives us is something that's almost like that. So for every x in that interval, with the exception of x star. X star is just not important because we know that it works there. There exists an x tilde, and that's the crucial point here. There exists a point x tilde, and all we know about that point is that it is between x and x star. So in the interval between x and x star. Such that the following holds. F of x is equal to TNF of x and x star plus, and here's the approximation error, plus f n plus 1 at x tilde divided by n plus 1 factorial times x minus x star to the power of n plus 1. Okay, so in other words, the remainder, Rn of x, is exactly that expression here, fn plus 1 at x tilde over n plus 1 factorial times x minus x star to the power of n plus 1. And of course, the downside of this is the error bound is not that explicit because we don't really know what that x tilde is. It might be anything between x and x star. We just know it exists. We don't know how to get it. So what we have to do in order to make use of that error bound, we'll have to find a bound for this expression somehow. And if we can do this, then this will provide a valuable error bound. If we can't do this, then it's not of a lot of use. So this is the crucial point. We need to bound this somehow, only knowing that x tilde is between x and x star. So this is not quite as explicit as we would have liked it to be, but it's not that bad either. And how we can find such a bound and how we can exploit this property, that is a point that we'll talk about in the examples, and those will be in one of the upcoming videos. And as usual, I'm confident I'll see you then.